So this is the persistence of vision globe. Persistence of vision is a concept that after eyes see an image or see any amount of light, they retain an after image of it for a 10th to a 15th of a second. So by a globe spinning so fast, it takes advantage of that, and that the LEDs are at exactly the same spot after every spin, and they do so more than 10 to 15 times a second. Therefore, it gives the impression of a constant static image that is either not moving, or in this case we actually tweak it slightly so it does look like the globe is rotating. Of course, we have 60 LEDs going down it, and they're all RGB LEDs, so we can address them individually and create any image or text we want. The way we created this text in specific is we wrote code in Python that can take any arbitrary image, convert it to 60 by 60, a 60 by 60 array, and then we'll go through every single pixel, pull out the RGB value, and dump it into an array that we send to Arduino or can display. To create text, we use Python code that converts arbitrary text to an image, and then we type it through the original code we had. So now slow it down so we can take a better look at the parts. What we have in the back here are two switches that control the power supply. So we have one that controls the power supply to the motor, and personally I love the fact that they're LED switches, so they light up when they're turned on. So this one's currently turned on to power the Arduino and the lights, and we'll turn it off. So we'll take off the enclosure. The reason we have an enclosure is for safety, so that kids are not able to physically touch it as it spins. And it was certainly necessary today. So let's look into the different pieces of it. First we have the buttons, which again control the power supply. In specific, we have the one on the left here controls a 12-volt power supply that goes to a motor controller. The way the motor controller works is it has 12 volts coming in here, which is controlled by the switch, and it's always coming in at 12 volts from our power supply. Then the motor controller, based on the location of the potentiometer, generates a PWM signal coming out of these two terminals. And this little chip is what actually generates it. The capacitors and resistors and diodes are for protection of that chip, and additionally they control for like flyback voltage, which is caused when the motor is actually spinning, it generates a lot of momentum. So when the motor stops, it has to release, because of momentum, it actually has a lot of magnetic field stored in the inductor inside, and as it releases back through these resistors and capacitors. But anyways, so as you adjust this, it adjusts the power that actually goes to the motor. The motor, using a sprocket on the end and a belt, drives the ring. And the motor is extremely powerful. We run it using about 15 watts of power, which is 12 volts, with a little over an amp. It's rated up to 240. The reason we bought such a powerful motor is because we wanted to make sure we can actually support spinning such a heavy weight at such a high rate. So now let's take a look at what's physically on the board and what is actually spinning. So of course we have the Arduino. We use an Arduino Way because it has a very high clock speed. It can store a lot of memory as well. So it can store all of our images that we actually want to display here, and it can actually send the signal to LEDs very rapidly. So the way we send the signal to the LEDs is through the SPI pins on this actual Way. So it has a clock pin and a data pin. And those send signals to all 60 LEDs, which are wired together from the LED strip we bought. And it can individually address every single one and send an R, G, and B value, which of course, ultimately sends a PWM signal over the chips that are internal to each LED. The entire thing is powered by 5 volts. Both the Arduino and the lights share exactly the same power supply. Now this is actually pretty tricky to implement, but here's how it works. We have the ground, which is passed up an aluminum rod that goes through the actual wood, and that comes over the top, and then through wires that are physically touching the axle. We cover them with conductive grease to minimize the chance that a connection is lost. So you can see as it spins, they're always in contact with the axle. That's how we pass the ground. To pass the high voltage, it runs through this wire here, and it touches the ball bearing. Inside the ball bearing, we have a wire that physically touches the ball bearing and spins around with it. That way nothing gets tangled. Now the system works pretty well, but of course, as it spins 10 to 15 times a second, there is always a chance that the power might be lost for a brief moment of time. That's not really an issue, except that if power is lost at all, it will reset the Arduino. So because of that, we have two capacitors which run in parallel, provide 160,000 microfarads. That is quite a bit of capacitance, and is enough capacitance to run these LEDs and the Arduino for about 2 full seconds. Note that these LEDs draw about 3 amps, and the Arduino draws about a couple hundred milliamps. So it's able to power this all long enough for it to reconnect on a subsequent spin and recharge the capacitors. Now we're going to display the test we just generated. And after we also demo images, we can display any arbitrary image simply because we go into Python code and we'll resize it and then pull their RGB values. But for this demo, we'll display the text we just generated, SpongeBob, and a globe of the world. So it just finished uploading. We'll go ahead and unplug the USB. So this is an example of what will happen when we run it. Prompts us for 3 lines. And then it dumps out the array. Now, we just have a flag that can either dump it to the console here for debugging so we can read it, or we can actually write it to the file. And that should cover all of it. And now we have SpongeBob. I don't know how easy it is to see in the video, but it's actually very clear when you see it in real life. And again, we have it rotating around just so it's kind of nice. And next